Hi everyone. Really glad to be here. Can you hear me well? Okay. My name is Efim Boieru. I am representing Encode Technologies. We do remote identity verification. We are one of the biggest companies in the US and other places, and we do technology in various fields related to identity, starting from face recognition, ending with documents, verification and validation, and so on. And the today's talk is about deepfakes, and more specifically about how we address them through adversarial research. So first of all, let's try to find out why deepfakes is a threat to remote identity verification, right? So before, when I joined Encode, for example, more than 4 years ago, the main threat related to faces was that someone would print someone's face or show on a screen or have some 3D mask, like, in Mission Impossible type of mask. So, and that was the main problem related to faces. And the main source of fraud, if you may. But since then, a lot of things changed, and fraud was more and more prevailing in the digital era. But how exactly this works? Because it's clear if you have a remote identity verification, like some SDK on your phone, it's clear what it means to attack with a printed face or a face shown on screen, but what it means to attack with the deepfake. So if we look at the regular user flow, basically there is a user and there is a device, and then what they do selfie capture or they do document capture, and then there is an answer, yes or no, but like a very clear flow. And what happens, how exactly a deepfake attack happens? It happens through digital injection, right? So there are different layers where digital attack can work or injection can happen. So one of them is if you have a rooted Android phone or jailbroken iPhone, and then you can install a virtual camera, and that means that basically your phone believes that this virtual camera is a real camera, and then you can basically submit a pre-recorded video or image, and for example our SDK would honestly believe that this is the input from the camera. And there are multiple ways how we try to detect that, right? So as I said, injection might happen on different layers, and that's why we address different layers. So one of the layers is user behavioral layer. It's basically related to how user behaves, how it types, how it moves the device, or for example, this is a very interesting research problem actually, does the video output correspond to the motion signal that you get from IMU sensors. So that's about user, that's the behavioral part. Then there's device trust. It's basically analyzing, is it a jailbroken or rooted device, or is it a completely legitimate one? Then there is camera trust. You analyze if the camera source is correct. I mean, you can do it in multiple ways. There are multiple properties of real cameras that are not satisfied with virtual cameras. I cannot go too much into detail, unfortunately, but this is the main idea. And then there is ML-based or deep learning-based approach to actually analyze the media that you get. Media means like images, videos, time series of motion data, depth maps, basically anything you can get. Let's actually see an example how it works. So I actually asked. This is a very simple example using like generic UI from Gemini. I just took my photo from LinkedIn, so any person can do that. And I'm asking Gemini to create a video of me, kind of in a neutral, with neutral expressions, looking towards the camera, in like home scenario. So it thought a little bit, and it did a pretty good job, I think, like very realistic. Like I think face recognition would be fooled by this video. So the video is there, it's ready. And then, okay, the next step is actually the device. So as you can see on this screenshot, you can actually purchase jailbroken iPhones, and that's it. If you have it, you can install a virtual camera. So that's what we did. And here you have already virtual camera installed and set up. And here the device already believes that the output from virtual camera is the output from the real camera. So when you click camera, you actually see the pre-recorded video of me. And that means that you can use any like third-party app and just submit this video, and they will believe that this is what is coming in real time from the camera. So that's how it works. It's pretty simple. I mean, of course, it's pretty simple if there are no layers of defense, but just for you to understand how it works in remote identity verification, a deepfake attack works through injections. And our analytics team actually made a pretty interesting analysis of dynamics related with AI. And as you can see, in general, fraud rate is roughly 10%, 15%, like the white bars, and it keeps growing, but not too fast. But if you look at the red line, this is the AI assisted, or the basically fraud that used AI in some way, and you can see that it is growing much faster, and it's already like quarter of the whole fraud, and by the end of this year, it's going to be half of the whole fraud using deepfakes or anything similar to that. Okay, so now we understand why this happens in IDV world, in identity verification world, but why is it a hard problem by itself? So there are various reasons, but let's try to look at the evidence. So this is very small plot. Unfortunately, you cannot see all the details, but let me explain to you. So we have the left plot shows the left plot is about images, and the right plot is about videos. So we asked 69 labelers, professional labelers who work for us. So that means that they are already experienced at detecting any kind of fraud, digital, physical, related to faces, documents, and so on. So we asked them, so here is a data set, 200 images, 200 videos. Tell us what is real, what is fake. I mean, of course, we generated these fakes, so we knew the labels, but labelers didn't know. So we wanted to see what is their performance, 69 people. And basically, I'm not sure if you can see it, but there are like gray dots, like a Pareto frontier that you can see there, both for images and videos, and they are from zero. So zero, like there are two axes here. The vertical axis, the y-axis, is the error rate on real people, and the x-axis is the error rate on deepfakes. So what you want to have is you want to have 0, 0. That means 0 error on real people, 0 error on deepfakes. And what we can see on these plots is that it is far from 0. It is actually, if you take the average labeler, and again, these are professional labelers, let's see the numbers. So the error rate for detecting deepfakes images is 50%, and error rate at with real people is 25%. So only 75% conversion and half of fraud is caught. Like really, you can say it's really, really poor performance. If you would rely on humans, you know, to kind of detect this, that would be not the best idea. And even if you take out of these 69 people, you take majority voting. So, you know, you have 69 people and like, okay, let's take the option for each image or for each video, let's take the option that is chosen by most of the people, if it's real or fake. Even in this case, okay, you can have a reduction in errors for real people. In the end, conversion will be 100%, but fraud detection rate will be as bad as it was before. However, yeah, we can also look at another point here, like there is a point of how our algorithms perform, and they are much better here, which is also interesting that if you compare humans versus algorithms, then I think for face recognition, for example, it was proved more than 10 years ago that deep learning based face recognition models are much more capable than even the best trained people at, you know, recognizing people doing face match. So now it's the same stage with deepfakes, that we proved based on this large scale evaluation that algorithms are much better than humans at detecting deepfakes. So first problem with deepfake detection is that they are really, really hard to detect. And imagine a scenario like our scenario, for example, at Encode, is we have millions or tens of millions of sessions every month, and some percent of it are deepfakes, but you never know which, and you'd like to know that, but you cannot use human evaluation purely because, as you can see, humans are not great at detecting deepfakes. So just taking data from production, labeling it, annotating it, and then training an ML model doesn't work. So, this is a regular, you know, ML approach, and in this situation, it just doesn't work. Also, a quick note is that there are 6 tablets in the next room, and we have a challenge. Which one is real? And did anyone try to participate? Okay, what was your success rate? 20. Okay, 20 out of 50. So it's like 25 reals and 25 fakes. You have 20. Okay, it's not that bad. Anyone else? Okay, so feel free to try after my talk, and see if you are better than our algorithms. Another thing is, okay, how fast, how quickly new deepfake generators appear. Yeah, when I say deepfake generators, I mean any new version, any new model that is able to generate a face. So what we did, we developed our internal agent that searches for new AI, like new generative models. It looks for on GitHub, on Hugging Face, on Telegram channels, on basically like on Reddit, on as many sources as possible to see if there is a new model or a new version, for example, of Gemini or some other generative model that can generate videos and images of faces. And as you can see from this plot, there are more than 400 tools that appeared throughout 2026. And in the bottom you can see the intensity of these tools. Yeah, we can say that the speed is more or less stable, but the problem is that they stack one on top of the other. So you cannot just, you know, take one tool and generate some data and then train your model, test it, and, you know, deploy, because there are so many tools, and that your model might overfit to this, and in the end, it's not a reliable and not a sustainable solution from ML perspective. So yeah, this is another problem, is the speed at which new deepfake tools appear. That's the second one. The third problem is how realistic they become. Yeah, this is similar to the first one that we touched on, but if we look at these examples, for example, so on the left-hand side, there is an image generated by Flux in May 2025. What we can see is this is a pretty easy image to detect by a human that this is not real, because on one hand it's too perfect, but on the other hand there are some features like some properties looking like computer graphics, and based on that you could potentially detect that this is not real. Then Nano Banana appeared, so there is September 2025, and this image, even though it's still kind of perfect-ish, it's much more realistic, much more convincing. The texture of the face, the light reflection, the simplicity, it's much closer to reality. And then Nano Banana Pro appeared, and that's again like, so you see May, September, November, there are just a couple of months between them, and look at this image. Like, it looks like a completely like legitimate photo of a guy in his room with messy background, like they didn't clean up their room, like a normal teenager, and you wouldn't ever think that this is not real. And this is already in November, like last year, so almost 1 year ago. And so imagine, like, if at this speed they increase realism, how do you keep up? You cannot just reuse the same approaches. You cannot just, oh, we have some transformer, whatever, we have some neural network, and we will be just, fine-tuning it every time when there is a new tool appearing. It doesn't work like that, because every single new tool becomes more realistic and harder to detect. So the same approach won't work. So that's the next problem that we have. And there is another big problem, that the fourth one is about agentic fraud. Let me explain. So on the left-hand side, you can see like a regular fraud that involves synthetic identity. It's actually similar to what I already described at the beginning. There is a person and like a hacker, a fraudster, and they like generate a synthetic face, for example, or they steal some ID or whatever, and then they try to go through the IDV process, and then they might get accept, then it's a success for them, or reject, and then they try to learn from their mistake and improve. So that is kind of normal scenario for a normal fraudster. What happens with agentic fraud, it's completely different. Basically, fraudster owns an orchestrator agent, and this agent does a lot of things, but in a nutshell, for example, it might have, so imagine that fraudster has a target identity. That means that there is one agent that searches all information in internet about this identity. For example, last name of their mother, or pet's name, or whatever, all these kind of secret questions, trying to find from social media and so on. So that would be one agent. Another agent would be generating prompts, and with these prompts, another agent would be generating images or videos of a target person. Like, imagine that you have one photo of this person, and then you can use multiple prompts to generate multiple videos of this person, looking at the camera in different conditions, outside, inside, and so on. So that would be another agent. And then what else? Then there is an agent that tries to understand, for this particular IDV vendor, which is the best way to do an injection. Like, you don't know in advance, So you try different approaches. So that would be an injection agent. And then you have all these agents working together, and they set up one attack, and then they get feedback from the system. Regardless of how secure is your system, you still provide some feedback information for the user, because you want to, like, it's always a trade-off between security and user experience, right? So that means that you need to provide some information, at least, like, for example, move closer, move further, make better lighting, turn on the light or turn off the light or whatever. So you need to provide some feedback to the user, and that means that this orchestrator or this orchestrating agent uses this information to have a loop of multiple attempts to attack the system. So that means that with agentic fraud, you can actually scale the number of attempts like to thousands in a matter of seconds or minutes, and this is enough to basically fool any defense that is out there. So these are the 4 problems that are related to deepfake detection in IDV, and yeah, when we realized all that, we were like, oh, crazy, how are we gonna defend against this, because it looks like almost impossible, and you can just give up. So yeah, that was the problem. And what we now understand is that our solution is adversarial research. What it means? It means that, first of all, we generate our own data sets, our own source of truth deepfakes. We do not trust external data sets, we do not trust people and so on. We trust only deepfakes that we generated on our own, because we completely control this process, and we don't rely on human judgment or external validation. So we build a very high variability data set containing hundreds of different generators. Okay, that's one thing. And that's a continuous process that we keep doing. But another thing which is important is that we have an internal red team that constantly tries to attack us, constantly tries to find under which conditions we stop detecting some deepfakes. For example, there is a new tool, a new image gen from ChatGPT, image gen 2.0, and let's assume that we can detect all those images. But are there some particular conditions when we stop detecting them? For example, if you change the background, or if there is a particular demographic group with which we struggle. So they try different ways to find the weaknesses and loopholes of our defense. And another direction which is extremely important is adversarial research. It's what we do, internal research that is basically attacking our own systems. And what we do is, I'm not sure how familiar you are with GANs, generative adversarial networks. Basically, it's like more than 10 years ago, the first models to generate images, these were GANs. And what they do is that there are 2 competing neural networks. One is generating image, and another one is answering, is it image generated by the first network, or is it a real image? So, and these 2 networks, they keep competing. Like a discriminator gets better, then the generator is forced to be better. If discriminator can detect everything, that means the generator needs to improve. And then if discriminator cannot distinguish between the real and fake, that means that it needs to get better. So this is how GAN works. And we decided to build an internal framework in our team. Basically, we have people who are adversarial, like they are actually like generative model, generative neural network, and another group of people who are defenders, so they are discriminators. This is the structure, like internal gun structure as we call it. And on one hand, we talk about this in terms of like the people, who contribute, engineers, but also we do autonomous frameworks that work this way. And in the end, what you get is a self-improving framework because you have one model that constantly attacks and tries to find new ways to attack, and then another model that uses approach, like sees all these weaknesses and then tries to improve itself. Beyond that, of course, we use independent red teams. For example, Social Proof Security and NetSpy, and they try to attack us with so many different attacks, like face swaps, synthetic faces, and so on, and also like some physical attacks and injection attacks of various kinds. So this is, of course, also very important, like having internal red team, having external red team, and having internal adversarial research team. Okay, but what particular type of attacks we actually do? So this is an example. This is an image that is generated by us, actually. Like basically, this is a deepfake, and what you can do, you can analyze fraudster. When a fraudster does an adversarial attack, they try to find a way that your model won't be able to understand that this is actually a deepfake. So you have as input a deepfake, and you wanna apply some changes that detector cannot detect it anymore. So there are like you have to start with simple things, like what we call it robustness adversarial attacks. It's when you do different types of compressions, cropping, resizes, adding noise, adding blur, and other simple computer vision approaches or image processing approaches. And here, as an example, you can see that, okay, if you do JPEG compression 90, then it's fine. But if you do it like heavy compression to 50, then detector is not anymore able to see it. And that is because of high compression, a lot of artifacts, a lot of patterns that you could see from a deepfake generator, they got lost throughout this compression. I mean, in the end, you can also detect that this image was compressed, so it's okay as well. You can still get it. But for example, you see if you crop the image, if you resize the image, then it doesn't really affect the detector. So this is one thing. Another thing that we developed is we developed our own agentic framework. Basically, one agent searches internet all the time, as I said, and it tries to understand, okay, this generative model, is it capable of generating faces? Okay, what type of attack this is? This is face swap, this is synthetic face edit, what exactly is this? Does it operate with images or videos? Does it provide hyper-realistic results or some cartoonish type of results? So this is the first agent. This provides candidates of deepfake generators that need to be processed later. Then there is another second agent, which actually takes, like for example, a new generator, like some model on GitHub, and it actually writes code and deploys this model on our premises and writes code to run this model. And then it runs the model. For example, if it's face swap, we already have predefined target and source faces that it needs to use, and it generates data sets based on this generator, and then it tries the performance of our detector on this data set. So basically a completely autonomous process to understand what is the performance of our detector on newly appeared generators in internet. And on the right hand side you can see like our leaderboard. Yeah, I had to blur out the names and numbers, but basically these are models that our agentic framework found and tested in our detector. And as you can see, there are a couple of models that really made a hard job for our detector. Yeah, but there are also two columns. You can see one blurred away column and another one. So this is basically the difference between two versions, and our next version has much less error rates on these generators. So there is some improvement, but in the end, the amazing thing is that this is completely autonomous, and yeah, you just don't need to do anything. You just need to keep track and monitor from time to time. Okay, but given this, like we understand that there are hundreds of new models appearing, like in a matter of several months. How do you keep up? How do you actually try to improve your model? And the answer to this usually lies into feature adaptation, because you don't have time to generate thousands of images and videos from each and every generator, especially when you have hundreds of them, because first of all, it's very slow. Second, it is gonna explode your data sets pretty quickly. And feature adaptation is the idea to adapt your detector using like much less samples, for example 20 to 30 samples, and yeah, one of the idea is to, like depicted on this image schematically. It is basically we can treat this image as embedding space of some detector. Each point represents an image. And for example, orange is diffusion-based synthetic faces. Yeah, greens are face swaps, and blue are real images. And imagine that you have a new generator, and this generator makes like leads to high error rate. Like you cannot detect all of them. That means that they get mixed up with real samples, so they get mixed up with these blue dots, with the blue cluster. And what you can do as a simple solution, you can just basically build epsilon vicinity around some of these samples, and just by rule decide that all of these are fakes. And this is already this is a very simple solution, but it already allows you to reduce error rate, I don't know, like by several times at least. And if you do it properly, you can. It's not gonna affect conversion or like a false rejection rate. So this is about feature adaptation. Another big thing, and I believe this is the biggest thing that I'm going to present, is how we build our internal generators. So as I mentioned, there are a lot of external public generators, and they keep becoming more realistic, and they appear very frequently. So at some point it's going to be really hard to detect them. So what is our response to that is building our internal generators. And the idea behind it is the following. So imagine you already start with some publicly available generator and your own data set. So what we do, we fine tune the publicly available generators like flags or that image or some other generators. We fine tune it on our data. And then even if our detector before had no problems detecting faces with these generators because they were fine-tuned on our data. They started generating images that are much similar to real users from production, and that's why the error rate becomes really high. In this example, it's 56%, which is crazy high. And then what you do, you generate images with this generator, you improve your detector based on this new data set, and error rate falls, like, for example, to 2%. And this is a loop that you can repeat as many times as you want. You basically build a new generator, then you generate a data set using this generator, you fine-tune your detector, and you continue and you continue. So that's the foundational idea that we present. Let's have a look at an example. So we start with a public detector, a public generator, and we fine-tune it on our data, on our production data of normal selfies of normal users. You can see here examples of the images that we get. I'm not sure if you were able to observe, but the initial images, they were very polished, very computer graphics generated, like very idealistic. And the last image is like very regular selfie, tired person, not really happy to do selfie. Let's try again. Let's try again. You see, like very perfect image, perfect lighting, and then it changes. It becomes rough and noisy. Yeah, unfortunately the screen is not really large. And on this plot you can see how changes the confidence of our detector. As you can see, in the first iterations, it is convinced that this is fake. This is like a deep fake. But as iterations of our fine-tuning continue, then detector is completely fooled. It believes 100% that this is a real image. And it looks like a real image. Let's look at some more examples. Again, the dynamics, how like basically publicly available generator becomes our generator adapted to our domain. And once again, try to compete. Now you understand much more about our generator and how deepfakes look like. Try to participate in the challenge. Maybe you'll have higher score. I tried myself. I have 45 out of 50. I tried it like in the morning. Let's see if you can beat. I mean, and also I remembered some faces, so for me it was easier. But yeah, this shows how you can actually. Yeah, why we do that? Why we do that? Let's look at this image. This is a little bit technical, but bear with me. So we took a publicly available detector. Like imagine this is some pre-trained model publicly available, and we look at embedding space of this model for different data sets. So the blue color represents our data from production, real users, like legitimate selfies from production. And all the other colors and dots, they represent public data sets. They might contain real images and also deepfake images. But as you can see, there is a very clear boundary between them. Our selfies and public data sets of deepfakes and real people. There are many reasons why this is the case, but the main idea is that there is a clear borderline between them. So we try to see what happens if we generate our faces. And these are the blue, or sorry, the purple and red dots. And as you can see, they overlap significantly with the real data that we have in production. So what we achieved by that is we were able to build generators that are that produce extremely similar images to images that we get from real users. That means we made a very, very hard task for our detectors to, to answer if this is real or fake. And if you think about it, like, this is actually the main goal, because if you are able to build the strongest, the hardest possible generator, that means that you can build the best detector. So, like, we challenge ourselves, and that's how we make a better defense. And this image, actually, this plot represents the perfect triangle of success. So basically, the left dot shows the error rate on the publicly available generator. So we assume that we already have very good performance on this publicly available generator, which is often the case. And then we fine-tune it on our internal data, and error rate becomes significantly higher. So our detector is not able to detect these images anymore. Like here we can see 31% error rate. And then we again train our detector on the data generated by this fine-tuned model, and the right dot represents the final error rate of our detector with the new generator. So basically, full cycle. Start from great performance, make it bad, then again improve your detector. So this is the main idea. So let me conclude my talk. So we realized that there are several reasons why deepfakes are really like one of the main threats for remote identity verification. First reason is that these tools appear really, really quickly. Second is that with every new generation of deepfake generators, they become much more realistic, and you cannot trust labeling of human labelers, even if they are professionals, because they are too hard. Even videos, which is interesting, I didn't point out before, but videos are also hard for humans, because before images were hard, now images are also like really, really hard to detect. And adversarial research is what we believe is an answer to this threat, and having internal red teams, external red teams, having internal adversarial research teams, then having a self-improving frameworks of discriminative and adversarial models that compete between each other, and few-shot adaptation to improve the model. And this way, by building internal generators, you can anticipate new fraud, new deepfakes, and not wait for new generators to appear in public. This is the end of my talk. Thank you very much for your attention. Yeah, that's QR code to my LinkedIn profile. Do you have any questions? Yeah, please.
So most know your customer systems will use videos for verification rather than images. You talk mostly about detecting deepfake images. Do you have any models that detect deepfake videos? And if so, are you looking at any physiological indicators in the deepfake videos?
Yeah, very good question. So the question was, do we handle video deepfakes, and also, if so, do we pay attention to physiological signals? So I talked about images because it's easier to talk about images, but we work heavily on videos as well. And regarding physiological signals, I would say I don't trust them. I believe that new generative models, they are able to fool any kind of physiological signal detector, and like for example blinking or other micro movements on the face. They become extremely realistic now, and I don't believe there is a lot of sense to try to use this as one of the main signals. This can be a supportive signal, but I don't believe this is the key.
What about skin color changes?
Yeah, so I am a true believer in pre-trained models. Basically, if you build a foundation model with a very large data set, then it can learn all these patterns by itself. I don't believe that you can build a model by explicitly showing these. Look at the color changes on the face or something like this. I think if there is some pattern, it will learn based on how you train your model. Please. It's hard to hear.
Over time, like the focal length of the images of the selfies, like got a lot more like realistic, in that it's less flattering. Do you think that is like a big part of like it being convincing?
Yeah. I think that might be the case, but in the end, you also do a lot of preprocessing. When you do training of neural networks, you do a lot of augmentations. So we try to do as many preprocessing as possible, so that regardless of the camera input, you can detect deepfakes. And we are lucky in this sense because we have customers from all over the world, and their users are also from all over the world, and they have devices like 15 years old phones and new phones and so on. So these focal length distributions are extremely diverse, and that helps a lot. Any other questions? All right, thank you very much.